For hydration, as the name suggests, you add water to it. They would react reversibly with water to give a 1,1 diol, or we call them geminal diol. You know Gemini, the zodiac? Gemini, so geminal diol. Both alcohol attached to the same carbon. The equilibrium position favors the carbonyl compounds for steric reason, except for formaldehyde. So for formaldehyde, this is the only case where the equilibrium prefer to stay on the right, the geminal diol. You can see from this chart here. So there are two different mechanisms for dehydration. One's the base catalyzed, one's the acid catalyzed. Now if you do not use a base here but use water, water is a poor nucleophile because it's neutral, and carbon here is not that electron deficient, so these two will not attract so much. But now you change it to a better nucleophile that can go in at a much better pace. So negatively charged hydroxide is very strong. It will go in to attack something that doesn't even want it and reacts. For this side, it's a different story. Basically, water is not that good, so you make the other guy wants it more. So what you do is now you add an acid to it to protonate to the oxygen here, so that now the O carries a plus charge, which will pull more electron density from the adjacent carbon. And so now this carbon feels very deficient in electrons, and that's why it wants the water even though it's not that good donor. So you see, pulling strings effect, push and pull. Okay, so we call this molecule for the compound here a gem diol or geminal diol, or the hydrate. Now aldehyde and ketone reacts reversibly with two equivalents of alcohol in the presence of an acid to give an acetal. And we can call it ketal if it's derived from ketone. So in this case it's ketal because it came from a ketone. 2 moles of this alcohol joins in here with some dehydration, loss of water molecules. You get this OO here. Alright, looks pretty scary sometimes at night. So if you only have one equivalent of the diol, it will yield a cyclic acetal. You see a diol, one equivalent, because it connects both ways, it clamps together from both sides, like chelates it, with water being lost. So here likewise, you see 1, 2, 3, 4, 5, 6 is a 6-member ring here. You get some funny looking feature. Now the reason why we apply these is because they are good protecting groups for aldehyde and ketone. What do I mean by that? Suppose I put a diol here, it become a acetal. So now this part here will not be able to be attacked by a nucleophile because this carbon is no longer a CO double bond. So now for this part, when I throw in some Grignard reagent, it is stable, it is inert. So we call this selective reactions, chemoselectivity in organic chemistry. Chemoselectivity. It means in a big molecule here, there are many functional groups, but we only choose to react with that functional group, so we're going to protect the rest. We cover them up first. Now recall that here, if we throw in some lithium aluminum hydride, it will just reduce all the way to the alcohol form. It doesn't stop halfway. Same for the ester. You go back to the alcohol. What we can do is we can protect the ketone here when we have a bifunctional group in a big molecule. Put this guy first here, protects it, and then now throw in the lithium aluminum hydride. This part gets reduced totally to an alcohol, and then this part still remains inert because we want to keep the ketone. So now we add back the acid to break off the acetal and get back the ketone. Do you see how it goes? It can't be done directly. There's no reagent that can do this. Maybe enzymes, but this is not within our syllabus. We are talking about organic chemistry in the synthetic lab. And also recall that there's no free hydride, but a hydride tags along to another atom like a borohydride or aluminum hydride. So nucleophilic addition, so hydride and your R minus, a carbanion ion, act as the nucleophile here and do a nucleophilic addition. You get the alcohol. For amines, amines are also nucleophile because of the lone pair here on the nitrogen. It goes in and prefers to do a substitution. So you get the imines, imine, or you can pronounce as this, imine, the Chinese noodle. Very delicious sometimes when they cook it well. Imine, and this is how it looks like. Double bond with the nitrogen here, with the elimination of water. So it's like, you see this, the amine, H2O comes off, the N just joined double bond in place of the oxygen initially. Voila. Likewise here, lone pair attack, arrow pushing, after that elimination. Voila. This is the detailed mechanism. Try to see, you should be able to understand this. Alright, so that's the end of this topic. I'll see you.